Canvas fingerprinting is probably the most misunderstood signal in this whole space. People know anti-detect browsers do something to the canvas. They know the word noise gets thrown around, and they assume more noise means more protection. It is almost the opposite. Done carelessly, adding noise to the canvas is one of the fastest ways to make a profile stand out instead of blend in. Today I want to explain, defensively and in plain terms, what canvas fingerprinting actually is, how detection reads it, and why the naive noise approach can quietly backfire on the person relying on it. Quick note on framing before I start. I run real proxy and cloud firm farms, and I test how these browsers handle fingerprinting for a living. So this is the layer I spend the most time on. I am going to keep this third person and defensive the whole way, how the technique works and how it is defended against, not a recipe for beating any particular side. What canvas fingerprinting is. Start with the mechanism because it is simpler than people think. A website quietly asks the browser to draw something onto an invisible HTML canvas element, usually a line of text in a specific font, plus a few shapes and colors. Then it reads the pixels back out and runs them through a hash to get a short string. That string is the canvas fingerprint. The site never shows the drawing to you. It just draws, reads, and hashes, all in a fraction of a second while the page loads. Why the canvas is so revealing. Here is why that drawing is worth anything. The exact pixels that come out depend on your graphics card, your graphics driver, your operating system, the fonts installed, and how your system does anti-aliasing and sub-pixel rendering. Two machines rendering the identical instructions produce subtly different pixels, and those tiny differences are stable and largely unique to a device. So a simple drawing nobody ever sees becomes a quiet, reliable identifier that ties your browser to a specific hardware and software combination. No permission needed. Part of what makes this signal so useful to trackers is that it costs nothing and asks nothing. Reading the canvas does not trigger a permission prompt the way a camera or location request does. The page just calls the readback methods, gets its pixels, and moves on. That means canvas fingerprinting runs silently on an enormous number of sites, and you never see it happen. It is passive from your side and cheap from theirs, which is exactly why it became so common. Stability is the whole point. Now the key idea that everything else hangs on. A real device produces the same canvas value every time. Reload after reload, day after day. That stability is normal and expected. A genuine user's canvas fingerprint does not change between page loads, because their hardware and drivers do not change between page loads. Hold on to that, because it is the exact thing a naive noise strategy breaks, and breaking it is what gets a profile noticed. How anti-detect browsers respond. Anti-detect tools take one of a few approaches to the canvas. Some inject small amounts of randomized noise into the pixels before the page can read them, so the fingerprint differs from the real hardware. Some spoof a fixed plausible value that stays consistent for that profile, and some try to block or restrict readback entirely. Each approach trades off differently between hiding the real device and looking like an ordinary one. And the difference between them is where most of the real-world success or failure lives. The random noise approach, the most common and most misunderstood approach, is per read noise. Every time the page reads the canvas, the browser perturbs the pixels a little, so the real hardware value never leaks out. On paper that sounds ideal, the true fingerprint is hidden. The problem is what it does to stability, and stability, as we said, is what a real device has, and this approach quietly destroys. Why perp read noise backfires. Think about it from the detector's side. If a script reads the canvas twice on the same page and gets two different values, no real hardware does that. A genuine device is deterministic. The same drawing yields the same pixels every time. So a canvas that shifts between reads or shifts between page loads within the same session is not hidden. It is waving a flag that says something is actively tampering with me. The noise did not make the profile invisible, it made the tampering visible. That is the backfire in one sentence. The consistent spoof approach. The better behaved approach is a consistent per profile value. The browser picks a plausible fingerprint for the profile once and returns that same value every single time, stable across reads and reloads the way real hardware would. This looks far more natural to a detector because it has the property that matters most. It does not change. The trade-off is that the value has to be believable and has to agree with the rest of the profile, which is harder than just scattering randomness, blocking readback entirely. The third approach is to refuse or restrict the readback so the page gets nothing usable. This sounds safe but has its own tell. Very few ordinary users block canvas readback, so a browser that returns an empty or clearly blocked canvas is itself unusual. You have traded a unique fingerprint for the smaller but real signal of being one of the rare visitors who blocks the canvas at all. Sometimes that is the right call. Often it just moves the anomaly somewhere else. The cross-check problem: canvas never gets read in isolation, and this is what people miss. A detector can compare the canvas fingerprint against the WebGL renderer string, the reported GPU, the platform, and the font list. If the canvas has been spoofed to look like one kind of machine, while the WebGL render string still reports the real GPU, the two disagree, and that contradiction is more damning than either value alone. A good tool has to keep the whole hardware story consistent, not just quiet the one signal everybody talks about. How detectors catch the lie? Modern fingerprinting scripts specifically look for the fingerprints of fingerprint spoofing. They read the canvas multiple times and check whether it is stable. They look for the statistical signature of edit noise. They cross-reference the canvas against every other hardware signal for agreement. A well-known open-source test does exactly this kind of consistency and lie detection, and it will happily tell you when a canvas has been tampered with clumsily. The point is that the naive defenses have known countermeasures, and detection has moved on to catching the defense itself. The entropy paradox. There is a subtler trap here worth naming. If your canvas value is common, it blends in but identifies you less. If it is rare, it identifies you strongly. A noise strategy that produces a wildly unusual value on every load gives you a fingerprint that is both unstable and rare, the worst of both. Unique enough to track within a session and inconsistent enough to look tampered with. The goal is not maximum randomness. It is a plausible, common-looking value that stays put. More entropy is not more safety here. How an operator defensively audits canvas. The practical audit is short and worth doing before trusting any profile. Load a public canvas test twice and confirm the value is identical both times, not shifting between reads. Check that the canvas story agrees with the reported web renderer and GPU, so the whole hardware picture is consistent, and confirm the value is not so exotic that it is unique on its own. Those three checks, stable, consistent, and not bizarre, catch the great majority of canvas problems that a naive noise setting would otherwise create. Audio and web play, the canvas cousins. Canvas is not alone, and treating it as a standalone problem is part of why people get caught. The same underlying idea, ask the hardware to produce something and read the result back, drives audio context fingerprinting and web glyph fingerprinting too. An audio fingerprint reads tiny differences in how your system processes a generated sound. A web glyph fingerprint reads how your graphics stack renders a scene and what it reports about the GPU. These are canvas cousins, and a tool that carefully handles the canvas while leaking a raw audio or web glyph fingerprint has left the hardware story half told. A detector reading all three together will notice when one has been managed and the others have not. The shared value trap. Here is a mistake that quietly undoes everything. If a tool hands every one of your profiles the identical spoof canvas value, then all of those profiles now share one fingerprint at the canvas layer. You build separate profiles precisely so they would not link, and the shared canvas value relinks them anyway, no matter how different their cookies or proxies are. A good implementation gives each profile its own distinct but stable and plausible value, so the profiles neither match the real hardware nor match each other. Sameness across your own profiles is just as dangerous as instability within one. Update drift on the canvas. A canvas setup that tested clean 3 months ago can start leaking without you touching a thing. A browser update shifts how the underlying engine renders. A detector updates its checks to catch the current generation of noise, or the spoofing method itself falls behind. Because none of that is visible from your side, it is easy to keep trusting a profile long after the ground moved under it. This is why canvas testing is not a one-time setup step. It is something worth rechecking periodically, especially right after any browser or tool update lands. What a good implementation looks like. Put together, a good canvas implementation is boring on purpose. It returns a plausible, common-looking value. It returns the same value every time within a profile. It gives different profiles different values, and it keeps the canvas consistent with the audio, WebGL, GPU, and font story around it. It does not scream randomness. It does not block readback and stand out, and it does not reuse one value everywhere. Boring, stable, and consistent beats clever and noisy every single time here, and the tools that understand that are the ones that hold up under real testing. Reading a canvas test correctly. When you run a public canvas test, know what you are actually looking at. The page will usually show you a hash and sometimes a uniqueness estimate against its own visitor pool. A hash that changes every time you reload is the instability tail we talked about. A uniqueness figure that says you are one in a very large number means the value is rare and identifying, and if the test reports a signature it associates with known spoofing, that is the detector recognizing the defense itself. Do not read a canvas test as pass or fail, read it as 3 separate questions. Is it stable? Is it common? And does it look tampered with? Because those are the questions a real detector is asking too. So the honest takeaway is that canvas protection is not about adding as much noise as possible. It is about looking like an ordinary stable device whose signals agree with each other. A tool that quietly randomizes everything is often easier to catch than one that spoofs a boring, consistent value. Which browsers actually keep the canvas stable and consistent under testing, and which ones leak tampering, is written up at antidetectbrowser.org, tested hands-on with no undetectable promises anywhere. If this cleared up why noise is not the goal, subscribe. Because next up I am walking through how a good anti-detect browser handles proxies, and why the proxy setup, not the browser, is usually what decides whether a profile survives. See you in the next one.